Hi guys, so let's go over Newton's first law, the law of inertia. Along the way we'll draw some force diagrams. We'll see how we can apply Newton's first law to different problems. And so here's the definition that's given in your book, is that Newton's first law, there exists an inertial frame of reference such that a body at rest remains at rest, or if it's in motion, remains in motion at a constant velocity unless acted on by a net external force. So a net external force. So we're going to simplify this just a little bit, and it's this part right there. If we have constant velocity, so just keep in mind that a constant velocity can be zero, or it could be not zero. So as long as it's not changing, and if the velocity is not changing, then that means that the acceleration is zero. And that comes out of, just our study of kinematics. So it's a constant velocity, the submodel of constant acceleration. But anyway, the acceleration is zero. So that's what Newton's first law is about. So it has two different ways that it can play out. We can have an object at rest. So this would be when the velocity is zero. And then we can have a not zero. So the object could be moving. So we could have some, velocity. Say it's sliding this way, like the bowling ball, moving along the floor or resting on the floor. So what Newton's law says, that if this is the case, then the net force on it must be zero. So it's not that there are no forces, it's rather the total force. So now we can talk about force diagrams. So if I think about what forces are acting on the ball when it's at rest, well, we're going to have the force of gravity, which we label with Fg, and is equal to the mass times gravitational acceleration. And then we also have the floor pushing back, which we call a normal force. Likewise, if the thing is moving, so we push the ball and then we stop pushing it, and then it's just going to roll at a constant velocity. We're still going to have the exact same forces, the force of gravity, as well as a normal force pushing upward. So what we have, all right, so Newton's first law boils down to the idea that if the net force on an object is equal to zero, then the acceleration is zero. Or vice versa. If I know the acceleration is zero, then the net force has to be zero. And this falls into two categories. We can have, like I said before, we can have a velocity of zero or a velocity which is not equal to zero. And both of these fall into the category we call equilibrium. Equilibrium. And we have two types. We have this one, which is referred to as static equilibrium. So it means it's not moving. And then we have dynamic equilibrium. But all it means is equilibrium, the net force is zero. So let's see how we can apply this. So suppose we had an orangutan hanging from a tree. Or hanging from a rope on a tree. So you have the tree like that, there's a rope, and then the orangutan is hanging there. And so it's not moving, so we know that the acceleration is zero, which implies that the net force has to be zero by Newton's first law. And so since it's hanging from a rope, we'll have some tension force up here, and then you're going to have the force of gravity acting downward. And now let's suppose that the mass of the orangutan is, I don't know what orangutans are, say 100 kilograms. Okay, so now we can use Newton's first law in order to solve this. So we would say, well, the acceleration is zero, so we know the net force is zero. Now we have to define our coordinate system. Everything in this case is going to be in the y direction. So we can just work in the y direction. So the tension would be positive, and then remember this sign means to just add up, plus the force of gravity, but the force of gravity is down, so it's negative force of gravity equals 0. So now solving this, we would see that the tension is going to be equal to the force of gravity. Now I know you could have seen that just in the picture, but this is how we do it mathematically. To calculate the force of gravity, that's mg. So the tension in this case would be the mass times g, where g is equal to 9.8 meters per second squared. So we get a tension of 100 times 9.8, which is going to be 980 newtons is our tension. So equilibrium. Let's do another one. Let's suppose we have so we have like a wrecking ball hanging from a cable, and then we attach a second cable to it, and then what we're going to do is we're going to pull this thing back and hold it so that it makes an angle here, theta. And so what I want to know is like what's the tension in this cable over here. So let's draw our force diagram. So we have a wrecking ball, and then we're going to have a cable going up in this direction. So we'll call that T1. And then we have a cable holding it in this direction. Call that T2. And then this thing has mass, so we're going to have a force of gravity. I don't know the magnitudes of these, so whatever. Let's say the angle is 20 degrees or 25 degrees. Okay, so now let's solve for the two tensions. Given a mass of, I don't know, let's say the mass is 500 kilograms. So the ball is not moving, so we know that the net force is 0. That's by Newton's first law. And what we're going to have to do here, because this is in 2 dimensions, we have x and y, we're going to have to break it up into components. But we can use Newton's first law in components. So we have the net force in the x direction has to be equal to 0, and the net force in the y direction also has to be equal to 0 in order for the total net force to be 0. So now we can break it out. So we need the forces acting in this direction. So I can see that I have a T2 here, but we have a component over on this other side. So we're going to have to draw that in. So this would be T1 in the x direction, and then T1 in the y direction. So I can see my x's are these T2 and T1 in the x. So let's go ahead and get those in there. So we get T1x, and then I'm adding, but this is in the opposite direction, so minus T2 is equal to 0. So I get that T2, if I move it to the other side, is going to be T1 in the x direction. So I'm trying to solve for the two tensions. Let's see, T1 in the x direction, I can relate it back to T1. You can see if that helps. So T2 is going to be T1 sine theta. But I don't know T1 and I don't know T2, so I can't solve this. So let's go over to the y. So in the y direction, I have two forces. I have this one, and then I have a force of gravity over here. So I'm going to get T1 in the y direction minus the force of gravity is equal to 0. If I move that over, it's minus because it's down. T1 in the y is equal to the force of gravity. T1 in the y, in terms of T1, is going to be T1 cosine theta is equal to mg. So here I know this, I know that, I know that, so I can solve for T1. And then I can take that quantity and then plug it in here and I'll get T2. So T1 is going to be mg over cosine theta. Plug in your numbers, you'll get a value there. And then you take that value and plug it in here and calculate. I'm not going to do that because I don't want to calculate, but we would plug that in there. So T2 algebraically is going to be mg over over cosine theta, sine theta. And I can simplify this. Sine over cosine is tangent. So it's mg tangent theta. Anyway, you can just plug in your numbers there. And that's how we'll deal with that. Let's do one more. So for the last example, let's do a couple different angles. Let's suppose we have, like a car or something, sitting on an inclined plane. We'll put that at 20 degrees. And then it's there's a chain attached like to a wall, so it's holding it in place. We're not concerned with friction. So we want to draw a force diagram. It's not moving, and so we want to figure out, I don't know, we'll make up some numbers and stuff, but I like how we would analyze this, and it's really drawing the force diagram that we want to get down. Okay, so inclined plane problems, you have to know how to draw these things. So we draw the inclined plane and put our angle here, 20 degrees. Okay, then I'm going to draw the car as just a big block, 'cause I don't care. Okay, so now we have to figure out the forces. So we have a couple here. There's three. One is the tension of the chain, which should be this way. So we'll call that tension. And then we're going to have a normal force. And remember, the normal force is always perpendicular to the plane. So that's our normal force. And then the force of gravity. And gravity always acts straight down towards the center of the Earth. So we would have the force of gravity act this way. Okay. So in this case, what we need to do is we're going to actually tilt our entire axes. Remember, our choice of axis and coordinate system is arbitrary. So what I'm going to do is I'm going to call x this way and y this way, such that y is parallel to the plane. I mean, x is parallel to the plane. It just makes the analysis a little easier. So you can see the normal is in the y direction, the tension is in the x direction. So it's just this force of gravity that I got to deal with and as an angle. And the way we draw it is kind of always the same. So we'll have one component which comes straight, like opposite the normal, and then a component which acts parallel to the plane because that's in the x direction. And then the angle always goes up here at the top. So that's my theta. And so we would call this FG in the y direction, and this would be FG in the x direction. So this type of picture we're going to draw over and over and over again. But now we can solve this thing. So since it's not moving, we know the net force is equal to 0. And since we're having to deal with components, we have to break this up into x and y. So we know the net force in the x direction is 0. And the net force in the y direction is also 0. So in the x direction, in this direction, we have tension. I'm calling down positive. So we have tension, and then we have this force of gravity down here. So it's going to be FGX, this one, because it's positive, minus tension is equal to 0. And then in the y direction, we have the normal force, which is positive, minus the force of gravity in the y direction. That's equal to 0. So this is all for our equilibrium. So we just break it up into components, set everything equal to 0. Now we can solve. So we'll see that the tension, if I move it over, I get tension is going to be equal to the force of gravity in the x direction. And the force of gravity in the x direction, in terms of the force of gravity, is going to be sine. So it's force of gravity times sine theta. Moving this over, we get the normal force is going to be the force of gravity in the y direction, and the force of gravity in the y direction from the triangle in our trig is going to be FG cosine theta. And from there, we can make up some numbers and plug them in. But that's the basic approach. So Newton's first law, components, and then we just solve for whatever we need. But know how to draw this picture, deal with this.